keeping right on with anatomy and functionality and locomotion and biomechanics, we have a great next talk with John Davenport. John, are you there? And John is coming to us, I think, from the UK somewhere. But let's see. John is has been a professional marine biology educator since the 1970s. He does a lot of biomechanical investigations, mainly of fish, sea turtles, penguins, marine mammals, has an incredible eye for detail. And I think this is the first time that he's doing an online seminar, and there may be a connection issue. So
yeah, we're getting a slow load on John's end. I just sent him a message to try and exit and come back in, and looks like he's doing so. Okay.
Yeah.
But that's lovely link through from Kate's talk there, because like John came over on one of those grants we got for you. I love those little grants; they're great. To just bring John over to do some dissections, and yeah, I learned a lot. I learned a lot from doing that, you know, and it's great because I particularly love the papers where you get an N of 1, because it kind of cracks all my friends up that work on invertebrates. So that you can learn so much from that looking through. But no, and also, yeah, John's kind of linked through with me and Tom from leatherbacks, jellies. So the whole circle's kind of gone round, which is really nice.
Yeah, yeah. And John is an excellent at dissections as well. So along with his co-author. Well, it's looking, we're getting that slow wheel there. So but I hope so. You've known John for a long time.
He was my PhD external examiner. And yeah, I remember that because I wore a 3-piece suit back in the day, and I got proud of John because he's a very dapper gentleman for doing that. But yeah, no, he put me through places, and then carried on with me and Tom on the leatherbacks, jellies, and all the rest of it. But
yeah.
But yeah, one of those guys, when you look through the literature, if it's from giant squid to limpets to bioluminescents to siphonophores, his just name is there, you know. So it's been great fun over the years.
Well, I'm wondering. I don't know if we're going to get John today, because his signal might not be strong enough to support clicking into StreamYard. Let's see. I'm wondering. Well, we might have to.
Okay, so John's just messaged.
Yes. What? He's trying to get in, I think. I think Joe's going to be working with him.
Okay, cool.
It may be a Google Chrome. He might not be using the right browser. So, but we've had remarkable luck so far. You know, no real technical glitches so far. So, oh, okay. Yep. So he, I think he just has to download Chrome, and we should be good to go. Yeah.
It's been the curse of the.
So, yeah. And for those of you who are looking forward to the art show, we had a slight detour from the schedule because we some of our talks have been running over, so we ran right through the break and no art show. But never fear, the art show will we had the art show sort of piecing out in different parts throughout the day. So it's now just being pushed a little bit to later in the day. So don't fear, it will be there, and we will see that, and we may just go right on to Tasha, and we'll possibly we can bring John Davenport back in after Tasha if we can work out the glitches. So let's just move on to Tasha, and John, I think you are the best one to introduce Tasha, since she has been your student. And hi, Tasha.
Hiya, how you doing?
Yeah, absolute pleasure and privilege. It's been a lot of fun. How long have we worked together on? 7, 6, 5? I don't know.
Something like that.
Probably the best PhD student I've ever had, so I can say that openly.
Very kind of you.
Real challenge, baptism of fire. Started to work on sunfish. We went out to Italy, a place where we get 500 sunfish a day, sometimes in bycatch, and Natasha was faced with the first year of her PhD of seeing one. So that was a perfect baptism of fire of, how, I don't know, they're so tantalizing as a species. Done some absolutely beautiful work on something that's fascinated me for a long time, is that weirdness of sunfish diet, and that little bugbear I had of the fact that I knew they weren't just eating jellies, and the fact that we get lazy sometimes as scientists. The world is divided into PDF and pre-PDF, and if you go pre-PDF and dig back into the the literature that's not in English as well, there was a lot of evidence in there that these were far more nuanced, complex critters than we'd given them sometimes credit for. But I won't say any more because I'm fascinated by this stuff. I hope you enjoy this talk. There's a lot of work that's gone into it, and good luck, Natasha.
Great, thank you very much. All right, so I'll just set up my share screen. Here we go. Oh, sorry. So for some reason sometimes I have a few issues with if my camera's running at the same time. So I'll just drop that off for a minute. But obviously, I'm hoping you can still hear me, and then I can share my presentation and all the nice pictures with you. Great. Yeah, so obviously, thanks so much for that lovely intro, John. That's very kind of you. So yeah, as John said, my name's Tasha, and I'll dive straight in thinking about sunfish diet. So to begin with, as you may have figured out, so I'm a marine biologist in John Houghton's research group, and my research focuses on the ecology of big fish and how we can use new research to guide conservation efforts. And alongside my research, I also really enjoy doing science outreach and making little short films about the natural world. And very recently, I was very lucky to be involved with the book, the Sunfish book, and I was the lead author on the book chapter about the diet and trophic role of the ocean sunfishes. And this is working alongside co-authors of John Houghton, Chris Harrod, and Ed Pope, which is a fantastic team to be part of. So as long as I can remember, I've been fascinated by our oceans, and they form this wonderful alien environment covering 2/3 of the Earth's surface and containing a multitude of bizarre oceanic giants. And alongside many people, I just love the strangest of all the fishes, that oceanic oddball that is the ocean sunfish. As John mentioned, we've been working on sunfish for a while, and I was able to spend my whole PhD working solely on ocean sunfishes, researching elements of their distribution, their diving, their anatomy, and that's why Kate's speech just now was just so fascinating. So I'll definitely be asking more questions about that. But mostly, we've been trying to unravel their diet, and today I wanted to share some of their secrets. See if I can get this video to go as well. Oh, maybe the videos aren't going to work, but I will make sure that they're working when we post this online. So although the sunfishes, we know that now, obviously, and everyone's talked about today, that they're these global citizens and they're well recognized across their truly enormous range. And it's strange to think that we still have so much to learn about them. We're still not really sure how many there are. We're still learning about where they travel to. And until recently, we didn't know that much about what they ate. And you might say, why does this matter? And of course, that's a really good question. There we go. So we all know that the oceans and their inhabitants are facing many challenges right now. And one of those is the reduction in marine megafauna and then the knock-on effects this has on marine ecosystems. And so more recently, research has discovered that marine predator biomass has declined by 90% over the last 50 years due to this backdrop of human-induced pressures. And data for sunfish suggests that hundreds of thousands of sunfish might be being removed each year. This is both in target fisheries for human consumption and also accidentally in bycatch. And so ultimately, if we don't know where sunfish fit in local ecosystems, we might be in for a nasty surprise as large numbers of these fish then disappear. And as has been mentioned previously, the sunfish are still often thought of as these unimportant, lazy jelly eaters. And this can be a dangerous assumption, as it often means they're dismissed out of hand. They're not included in any conservation management plans anywhere in the world. But in more recent years, with more research and more data, we've actually been able to dispel some of these long-held myths, as we've been hearing today, such as new studies that have been shown they can travel these huge distances, traveling over 27 kilometers a day against prevailing currents. We know they can dive to over 1 kilometer deep. And there's been hints in the ancient literatures, as John said, that their diet is much more varied than first thought, which indicates this more important role in ecosystem functioning than previously known. And of course, these kinds of data are vital for fisheries management and conservation action, as to design sustainable, effective measures requires data, really strong, robust data, enabling us to model and understand these complex marine systems and answer questions such as, how do marine food webs work? Or how can we assess fisheries productivity? And to create these amazingly complex mathematical systems that can help to create such new protective measures, we often just need these simple inputs, the basic baselines about marine species, such as, where does this species live? What does it do? And of course, what does it eat? It's quite surprising how difficult it can be to answer these seemingly simple questions, and how little is known about some really popular species. It's become one of the greatest ironies about marine research, how little we know about some of the biggest and most charismatic fishes in our waters. And this might be due to a lack of commercial interest, or the difficulty of studying animals that tend to remain off-site, out of sight beneath the waves or offshore. But now, obviously, scientists and management teams and conservationists are trying to fill these knowledge gaps for management, to understand more about the ecology of all species and how they fit together. So when it comes to looking at food webs and ecosystem functioning, it's really helpful to know who eats who in an ecosystem. But how do we tell what a fish eats when it's out of sight? So traditionally, we would collect dead fish and look in the gut contents, but this gives quite a messy snapshot of recently consumed items, maybe just the last meal or two. And it can be difficult then to piece together the whole picture. Also, if your fish is eating the softer, more easily digestible prey, such as jellyfish, these are broken down so quickly, it can be hard to find evidence of them in stomach contents. So it's not so helpful for us with the sunfishes. And we also know that because the sunfish are listed as vulnerable, collecting dead specimens is not always an option. So sometimes we need a more modern or perhaps a more ethical approach. And this is when we turn to chemistry. So we all know that you are what you eat. And so your diet is reflected in your body chemistry. Now, of course, this means that we can use chemical techniques such as stable isotope analysis to look at the chemical makeup of sunfish tissues by collecting just a tiny fin clip from a sunfish fin, and then we can release the fish again unharmed. So this tissue sample can then be analyzed and can be compared to the chemical signature of a whole host of differing prey items. And from this, we can then reconstruct the sunfish's recent diet. We can identify differing prey groups and, most importantly, how much of each group has been consumed. So this figure shows the output of our sunfish stable isotope study. And we can see on the isotopic data plot here on the left of the screen. Now, this shows the average proportions of differing prey groups of sunfishes from the Mediterranean Sea. And these sunfishes have also been grouped by size class, you can see in here. And from this, we can see how their diet varies as they grow larger. So even though these size classes aren't hugely different, we can actually see a change in diet very quickly. So just to run over this figure, if we look at the bottom x-axis here from left to right, we've got differing groups of prey or potential prey. So here we've got the pelagic zooplankton, so obviously that includes our jellies, and obviously the like, so we've got anything gelatinous in there. For the benthic grazers, that's things like snails. The scavengers, things like shrimps. The sessile filter feeders, that's your mussels and oysters. And then finally, we put in fisheries discards. These were locally dumped discards of deep water, fast swimming fishes that we wouldn't expect to see in a sunfish diet. So we gathered examples of all these potentially available prey to create a reference library of the local ecosystem. And then we then compared these to see the proportion of these groups in the sunfish's diet. So up here you can see on this axis, we've got the vertical y-axis, we've got proportions. So that's actually the percentage here from 0 to 1. So that's from 0 to 100% of different groups in the sunfish diet. So we compared these across different size classes. So we've got the top here, we've got the sunfish of less than 50. In the middle, we've got sunfishes of 50 to 75 centimeters. At the bottom, sunfish greater than 75 centimeters. So the sunfish in this top group are the smallest ones that we looked at, and it seems that they're eating roughly equal proportions of differing prey groups, including the zooplankton, the benthic and sessile taxa, and they're also potentially scavenging on the discards, and that was a bit of a surprise. But then, as we move from these smallest sunfish with the mixed group to these larger size groups, we see things starting to change a bit. And by the time we get down to group C, again, the largest category we had in this study, we can see in particular the proportion of pelagic zooplankton has really increased. So, for our smaller sunfish, it's about 30% of dietary contribution. By the time we get down here, it's nearly 70%. And that's a really pronounced dietary shift. So this stable isotope method was also compared to further dietary data, such as that collected by animal-borne cameras, as you've seen already, of sunfish eating jellyfish in the deep, gut content analysis, and DNA barcoding, which is another fascinating way of looking into these things. And this builds an amazing evidence base on sunfish diet, which really helps to place sunfishes in the marine ecosystems and around the world. So overall, this combined evidence has again shown that when the sunfishes are smaller, as you can see in these initial pie charts, they have a much more mixed diet. We've got a range represented here of crustaceans and molluscs, even some fish species. And as you can see, more and more of these pie charts made up of the white elements, which is indicating a high proportion of gelatinous prey. And of course, this gelatinous prey isn't just your scyphozoan jellyfish. There's all kinds of gelatinous taxa, as Tom mentioned before, siphonophores, ctenophores, maybe salps. And so the sunfish grow larger, and then more of their diet is made up of this jelly. And so it seems the very largest sunfish exist on a purely gelatinous diet. So what does this really mean in terms of understanding the sunfishes? Well, these combined data suggest that sunfish have a more interesting and important role in local ecosystems than previously thought. We have this combined evidence that sunfish can eat a huge range of items, from algae and jellyfish to crustaceans and molluscs and sponges and fish. But the change in diet as they grow larger is also of huge interest. This suggests their ecosystem role changes over time. And so we can then link this to different behavioral patterns, such as when some smaller sunfish are seen schooling in large numbers in coastal shallow waters, where it seems they have this broad diet. And then as they grow larger, they appear to become more solitary. And then we can see they're moving offshore, where their diet then shifts to include this more and more gelatinous prey. The images here were all taken from a camera attached to an ocean sunfish from a study by Nakamura. And we can see here a fish's eye view of the open ocean. And so aside from this first image, which shows an encounter with a blue shark, mostly this sunfish sent back pictures of the potential prey on offer in the open ocean. There's so much jelly out there. And so overall, it really seems that by taking all this different evidence together, the biggest bony fishes on Earth are surviving on this mainly jelly diet, which seems pretty incredible. And this dietary shift over time to this lower energy density gelatinous prey might seem strange at first, because typically as an animal grows larger, we would expect it to increase in ability to tackle bigger, more valuable prey. But of course, the sunfish doesn't go down this route. And now we think we know why. Now, firstly, there's a lot of gelatinous prey in the open ocean. Overall, the total biomass of all gelatinous animals in the sea is estimated to be over 38 million tons. And as we all know, even if you keep snacking on low-calorie foods, it still adds up. And it also really appears across the marine food web that many species are making the most of this incredible biomass of readily available, easily digestible prey, including birds, reptiles, and many other fishes. If we consider that the leatherback turtle, which can reach 900 kilograms, they're obligate gelativores. And this means they survive on a purely gelatinous diet, where an adult turtle can reach its daily energetic requirements by feeding on tiny jellyfish, weighing just 4 grams each, and it can reach this daily energetic requirement in less than 4 hours. Now, put in this context, maybe the diet of the sunfish doesn't seem so strange. We have modelled the energetic needs of sunfishes, and it appears from the initial results that the larger fishes may be more energetically efficient than smaller ones. They will have a lower metabolic rate, and so they may not require so much energy per unit mass to survive. We must also consider that these big fish won't have the same energy demands for growth as the smaller sunfish. They've already reached a huge size, and so by this stage, it may be more about maintaining rather than adding to their bulk, and they might not need so many calories for their daily energetic demands. It also appears that the energetic value of gelatinous prey items might have been significantly underestimated, as although the typical energy content of a jellyfish is relatively low, it's been noted that sunfish are really picky eaters. They target the most energetically dense parts of their jelly prey, such as the tentacles and gonads of jellyfish, for example. And this selective feeding, particularly if it would occur in a dense bloom, offers a similar energy gain to that of a fish-based diet. So this sounds strange, but again, if we think of it as something like the jellyfish caviar, maybe it makes more sense, eating these tiny little energy-rich eggs which boosts their calorie intake. But again, it's worth thinking, why does this matter and how can this help? But now we have a better understanding of what the sunfish eat, we can start to piece together what might happen if they're all removed en masse, particularly as it seems that they might have this important role as predators and scavengers across local ecosystems. So we can now start to suggest that their dietary needs might dictate their movement patterns, as smaller fishes are feeding primarily on nearshore coastal prey in shallow waters, whereas the larger fishes are mostly targeting pelagic gelatinous prey offshore and in deeper waters. And all this information can then be used to understand the fish and factor into management plans. In particular, for sunfish management, we really need to address bycatch. Of course, anything we can do to help fishermen avoid these sunfish will be welcomed by both the conservation and the fishing communities. And so the sunfish are recognised by the IUCN as vulnerable globally, but they're data deficient on regional scales. And so by offering new data and building this evidence base to understand the sunfish diet, we can try to help reveal their ecosystem role. This means we can help predict the ecological consequences if sunfish numbers continue to decline and provide that essential baseline data for conservation and fisheries teams so that sunfishes can be included in ecosystem models and ensure their sustainable management for future. Unraveling the diet of marine species is a complicated task, but this may help us to shine a light on how and where the sunfish move between differing habitats as they grow larger and to avoid bycatch. And overall, these new insights have revealed a previously unknown, wider-ranging diet in smaller individuals and significant shifts to their ecosystem role. So in summary then, it can be difficult to imagine the global ocean without this charismatic group of globally distributed predators with their unusual life history and their varied ecological role. But as demands on the world's oceans intensify, further insights into the trophic role of all fishes are urgently needed to ensure sustainable management. So by highlighting these efforts and working together to better understand the trophic role of marine fishes, we aim to boost the knowledge of sunfishes and support a more sustainable future. So that's all from me, and I'd just like to thank the other authors on the sunfish dietary paper, to John, Chris and Ed for their incredible support, to Tierney, John and Graham for editing the whole sunfish book and bringing us all together, and of course thanks to everyone for organising the symposium today, Tierney and Joe and John. And yeah, thank you very much for listening. If you've got any questions, please do fire away, or you can catch me on Twitter at Sunfish Research or at Swimminghead. So thank you very much.
Oh, thank you. Thank you so much, Tasha. Let's see if we get you back.
Okay, there we go.
Yeah, no, just great. Absolutely great work. One question that comes to mind is, we see this shift in their teeth. What do you think is going on with their pharyngeal teeth?
Well, see, that's something that I think is particularly fascinating, is that I wonder at what stage the pharyngeal teeth really develop, whether they're present in really small sunfish. That's something I'd like to speak to Kate about, because my thoughts would be if they're feeding on potentially hard-shelled prey, like some of the molluscs, the crustaceans that it really seems that smaller fish might target, would that be damaging to these quite delicate pharyngeal teeth? Do they need them at that stage, or do they maybe just develop them later on? I think that's something I'd really like to learn more about.
Yeah, because they are really long and claw-like.
Yeah, they're like little cat's claws.
They're like little cat's claws, yeah. And they can. It seems like they're better at sort of digging into gelatinous play.
Definitely.
Yeah.
Yeah, the holy grail for I don't know, for you, for me, something we got into your thesis, we haven't got into press yet, is that whole shift to gelatinous prey, because there's double-sided argument. One is, okay, that's kind of cool. It's like we all like to live on, say, a fancy steak, but toast is more available, so it does kind of make sense in that context. But there's also, I wonder, can they, if you are a giant behemoth of a weird looking, slightly odd center of gravity creature, like the idea of like a 2-meter molar face down on a rock grazing on, microalgae is a bit weird. Maybe it just biomechanically doesn't make sense at that kind of stages. Well, there's probably not a singular answer, but I think, biomechanics, anatomy, combined with your dietary stuff, there's something. I don't know where your head's at with that, but
I'd be interested to find out where their center of buoyancy is, because I've seen some images of smaller sunfish head down, and I think it was in a net somewhere in Japan where they were being fed as like an aquarium keeping point, but I haven't seen images of big ones trying to feed face down or head down with that kind of angle. I'd be interested to see can you manipulate that in aquarium settings, or I don't know, that could be something we could look into maybe in captivity.
That's a really good point, actually, Michael. Howard would be a great person to.
Yeah, I'll have to ask him.
Like, if you did have a sunfish in a tank with just bait on the bottom, do they go no, or can they biomechanically do that?
Yeah, well, I actually, when I first started at the Monterey Bay Aquarium doing some research in the early 90s, made this little contraption to look at where the center of buoyancy was in relation to the center of mass. And they're almost on top of each other, but I could only use little small ones. So it would be really interesting to see how that shifts as they get larger. Because you don't, that sort of like downward, I don't know. It would be, I think you could model it. You wouldn't have to make the contraption. It was like this molded torture device that was really horrible looking. With fluids sticking out. It was the dead ones that the sea lions had helped procure.
It might be one of those questions that you get to through a logical kind of working through and discounting potential hypotheses, and process of elimination might be the way to go. Lovely talk, Tasha, by the way. That was really good.
Thank you.
Yeah. And great outreach work that you're doing there too. And just a very special shout out to Natasha and Lawrence Eagling, your second half there. Really indispensable for putting the book together. The two of you have just been terrific, as well as the little short video to promote the book. So I'm really just so grateful to you guys, and good luck on your filmmaking endeavors that are
Thanks. No, it's been a real pleasure to be involved. Thank you very much.
Yeah.